I want to thank the organizers of the conference. So, and my advisor is Professor Maria Athanasiou, and I'm going to talk about axially symmetric mean curvature flow. So, I'll just give a brief introduction to the flows and look at the picture of an axially symmetric case and go through the notation and give a couple of estimates and then do a part result of my thesis. So, mean curvature flow is it gives this equation where x is the position vector and h is the mean curvature and nu is the outer unit normal. So we have, in this case we take the outer unit normal if it's a compact surface. And we have an n-dimensional hypersurface, and yes, so everyone knows this. And this is the axially symmetric case. Now we are looking at an axis and two parallel planes like this and a surface of rotation with orthogonal Neumann boundary data. So these angles are 90 degrees and that's the thing that we are looking at. And now this similar thing has been done by Rescaling in his paper for asymptotic behavior of singularities. Now here we are not imposing any restriction on the mean curvature. It can be positive, negative, zero, whatever. So, and the question we are going to address is, can a singularity develop if the mean curvature is bounded for all time on the hypersurface? So if the mean curvature is positive, then there's no question at all because we know that so h is a mean curvature and A, if we say A is the second fundamental form, the second fundamental form is less than C times h. So there is some thing like that. So therefore, let's go to the next one. So the evolution equation for A squared on h squared. A squared is the norm of the square of second fundamental square of the norm of the second fundamental form, and this is bound. If you look at the evolution equation, you get a squared on h squared less than a constant. Now we can't have this. We can only make use of this evolution equation if h is positive. In the event h can be zero, this doesn't make any sense. So therefore, we have to look at something else to see whether a singularity can develop or not. Now the notation. So y is the height function. So when we looked at the curve like that, y is the height function, and we have the Neumann orthonormal boundary condition. So on the two sides we have y dash. So it goes from A to B. So the x-axis is the axis of rotation, and at x it goes from A to B, and then the y dashed A and y dashed B is 0. So we have the orthonormality, and this is the standard basis in Rn plus 1, I1 to In plus 1, and we introduce a local orthonormal frame on MT. Now the way we introduce is, so now if you remember the curve was going like this. Now τ1 here is the orthonormal, is the local coordinate that's going like that, and τ2 is always pointing inside to the it's inside the screen, and P and Q are these. Now this is defined such that we get the gradient in the sense on the curve, the y dashed on the curve is Q1P. And P is also one of the principal curvatures that is going around the circles. That's the principal curvature around the circles. And K is the principal curvature around this curve of rotation. So that's K. And we have the A squared is K squared plus n minus 1 P squared. And H is, this is the mean curvature, and this is the second fundamental form, so K plus n minus 1 P. And now we introduce another little thing, omega. Omega is, if we have the surface like that, can I draw, I think? Maybe, it doesn't matter. So if we have the surface like that, so omega is a unit vector pointing always like that to the curve. It's a unit vector which is used to define the gradient function. So V is omega nu and minus 1. So that's the gradient function. So now two estimates that's going to be useful for us is this. So these are the dy by dt is that, and dv by dt is that. So if we get d by dt dy, then we get this, and now v is a positive thing and y is a positive thing, so that's negative, and that's the gradient term, and therefore so we get vy is less than a constant. That's one of the estimates, and the other estimate is the d dt k on p. K on p again are the two principal curvatures. K is the principal curvature along this side, p on the circles, on the axial symmetric case. So you get k on p is less than that as well. And if now we are looking at the case where h is bounded, if h is bounded, then you get mod k on p less than a constant as well. So that's important. Now we use the rescaling by, similar to Huysken's in Australia, and the idea of the rescaling was given to me by Professor Huysken when I was visiting him. So the rescaling is this. So we have this surface here. We pick the maximum point at a time which the maximum of a squared occurs. And then we go on to the axis of rotation. That's the point. And then we rescale, and then we blow up on that by the value of the maximum second fundamental form. So it goes boom like that, and then we look at the rescaled surface. So that's the rescaling. And so alpha I is the maximum of modulus of A, modulus second fundamental form, and xi is, so if we go back, so xi is this point. Xi is the corresponding point of that. And so when we rescale it, the tildes are the rescale surfaces. We rescale it from this point, from the projection below onto the axis of rotation, and then we multiply it by alpha I, so we get this full blown up thing. And now the time is, we have a different rescale time as well. Tau is that, we'll get onto that later. Now with this rescaling, the rescaled mean curvature h tilde is alpha I to the minus 1. So now note that if we have a bounded edge, alpha I, and now the way we are going to prove this is we are going to assume that a singularity develops. And then we rescale and show that one of the estimates we had below, or we had above, would not satisfy, would not be satisfied on the rescale surface if a singularity develops. So if a singularity develops, this alpha I would go to infinity. And this if this h is bounded, this h tilde would go to 0 on the rescale surfaces. And that would give us a minima surface. And this a tilde I is alpha I minus 1 to the a. And this would mean that a tildes are bounded by 1 all the time on the rescale surfaces. So, and when we look at these, the dd tau xi tilde, the rescale surfaces, move or evolve by mean curvature as well. So, but that is dd tau. Now, if we look at how this looks like, now we have two parameters, I and tau. So, for I equals 1, so that is we have the alpha I, which is for that I, and then so the time tau goes from 1 minus alpha I squared t1 to that. So the time interval changes, the time interval tau changes, and for each I there is a flow of the surface, and the surface flows. So that's the flow of the surface that way, and that's different I's. Now we want to get a convergence. The way we can get a convergence is we want to get a convergence in this direction, when I goes to infinity. For a fixed tau, we want to fix some tau and then go down and then get some converging surface. Now, one of the things that happens when we rescale is we rescale, and then the first surface may be like that. Say the flow is axis of rotation, and we have the first surface like that, and the second surface goes up, and the third surface goes up, so it goes up to infinity. We want to, we show that it doesn't happen in this case. So we show that by the modulus of second fundamental form, that A is, this is k squared plus n minus 1 p squared. Because we previously had the mod k on p bounded, that was one of the estimates that we had. So 5 minutes more, okay. So mod k on p bounded, this would be less than a constant times p. Now p is less than y minus 1. That is by just definition, by writing it out, you get that y minus 1. And therefore, so you put that alpha i's, and the same thing in the rescaled surface remains. These estimates, because of the rescaling, it doesn't change this type of estimate. So ai tilde is less than the same constant c, yi tilde minus 1. Now, well, where the maximum curvature occurs, that's at tau equals 0, that ai tilde is equal to 1. The maximum second fundamental form A is always less than or equal to 1. So the maximum one is 1. So therefore you get that is equal to less than this, and because that's 1, you get this y tilde. At the maximum point, the height is less than this constant. So there is a part of this surface that remains that is not blown to infinity. Because of that, because it's not part of the surface is not blown to infinity, it doesn't go up the full surface, and also because the rescaled surface, the second fundamental form of the rescaled surface is bounded, we can get convergence by standard methods. So this is less than 1, and because this is less than 1, we can get a gradient bound on a small compact domain, and then use Arzelà-Scolli to get a convergence subsequence in a small compact in a compact domain. So now on this compact domain, because previously from the equations, this h tilde is equal to 0. So that would mean it would be a catenoid. That was the one we had because h tilde was equal to alpha I minus 1 times h, and alpha I goes to infinity, so alpha I minus 1 to the power minus 1 goes to 0, and h is bounded. So h tilde is 0 on the limiting hypersurface, which makes it a catenoid. But the problem is, on the catenoid, the other estimate we had, Vy less than c, does not hold. So therefore, we get a contradiction. So, so just saying that again, we assume singularity develops, and then rescale and find out that the rescaled surface the limiting surface will be a catenoid. But on the catenoid, one of our original estimates does not hold. So therefore, that's a contradiction. That would mean no singularity would develop if the mean curvature is bounded. Yeah, and that concludes my presentation. Thank you. Yeah, should I write on this, or we annotate? V was, V was omega nu to the minus 1, where omega is, if we had something like this, omega is actually this unit vector. That's omega, and nu is the outer unit outer normal. So v is equal to 1 plus y dashed squared to the root. That's the gradient function.